Let's continue to explore this open loop and closed loop systems. And in this case, what I want to look at is steady state error. Okay, so let me just remove the closed loop system from the scope for now, and let me just change this gain to 1, and let's take a look at what the output looks like. Okay, let me do one more thing. Let's try to connect this to the input so that we have the input as well on the scope and we can see it. Okay, so let's run this. And what you can see is that this is the input that we have, and the output after some time reaches the input. It reaches exactly the value of the input. So the steady state error, the error after the output stabilizes, is 0, right? So the output reaches the input. Now what happens if I change, let's say this is my system, and let's say as I keep using my system, as I keep using my process parameters change a little bit. Okay, so instead of 0.1, this becomes 0.9. So what happens to the steady state error now for the open loop control system? Oh, the so this is the input, and the output actually stabilizes at around 0.9 instead of 1, right? It doesn't reach 1. So as the process changes because of environmental conditions, because of wear and tear, there could be various reasons. You cannot expect a process to function exactly as it was when it was new. So as it changes, your steady state error starts changing. Now, how can you make the steady state error 0? One way to do that would be to change this gain. Okay, so I could put, I'm not sure whether I can do that, but let's try. Okay, oh, actually, I don't want 1 over 9, I want 1 over 0.9. Uh, and let's run this again. And you can see that once I change the gain, the steady state error again reaches 1. So the basic idea is that if the so if I change this gain, I can make the steady state response 1. But now this is not a very comfortable thing. Every time you run your machine, you will have to adjust your gain so that your steady state error becomes 0. That's not a very nice way to use a machine, right? So let's now try and see what happens with the uh, closed loop system. And what we will find is that the closed loop system actually is able to keep the steady state error much closer to the input, no matter what the variation in the output is. Okay, so let's take a look at that. Okay, I'm going to take this away. What I want to do is I want to get a signal. Oh, wait a moment. Sorry. So let me connect that here, and I want to connect another input to this scope, and you should get that there. And now let's take this and connect it back here. Okay, so one of the inputs is going to be the closed loop system, one is going to be the open loop system, and let's change this gain back to 1, and let's change this gain back to 1. Let's change this gain back to 1. Okay, and we need to change this gain also back to 1. So now these systems are exactly identical. Let's run this and see where you get the steady state response. So you can see that this yellow line is the trace that you get for your closed loop system. So the steady state error is quite high. The final value is 0.5, so there's an error of 0.5. This orange line is the steady state error for the open loop system, or it's the trace for the open loop system, and you can see that the steady state error is 0. Okay, now what happens as I increase the gain in the closed loop system? As I increase the gain, what you should find is that the steady state error keeps reducing. So can you see that from 0.5, the steady state error has now become around zero point 0.1 or so. If I still increase this gain, you would see that the steady state error becomes still smaller. Okay, now it's very small here. Okay, so as I make the gain of my closed loop system higher, the steady state error becomes smaller and smaller. Now let's take a look at what happens if the parameter starts varying. So instead of 1, let's say our process gets some variations, some wear and tear. There are some changes in the environmental condition that change the transfer function of our process and make it 0.9 over s plus 1 instead of 1 over s plus 1. So what do you get at the output at that point? You see the open loop response has changed quite a lot, but the steady state response error for the closed loop system has not budged even a bit. So basically, in a closed loop system, what you can do is you can change the gain, vary, and adjust the steady state error. And then it doesn't matter how the system function changes, how the process parameters change. The steady state error is going to remain at that particular value. So let's go to another value. Let's try 0.5, which is quite a bit of a change, right? And let's make this also 0.5, and let's take a look as to what happens to the steady state error of the two systems. What you expect is that the steady state error of the open loop system would have changed substantially, while the steady state error of the closed loop system wouldn't have changed by much. So let's take a look, and you can see that the steady state error of the closed loop system, it has changed a bit but not very much. But the steady state error of the open loop system has come down. The steady state value has come down from 0.9 to 0.5. So the error is 0.5 here from the 0.1 that was before. So what does this tell you? What this tells me is that the closed loop system is able to maintain a constant steady state error irrespective of the changes of parameter of the process, unlike the open loop control system.